Yeah, so no pressure on that introduction. Yeah, on the name HACMs, they made me put the name Cyber Military Systems in the name so that when congressional people were kind of scanning down the list of projects, they would come to that and they would be like, nope, these are not the droids we're looking for if we are looking to harvest funding for something else, and go on to find some other program that they might want to cancel if they were canceling it. Because when we started the HACMs program, they thought it was going to totally fail. And so they wanted it to be not something that would be a target-rich environment for canceling. But I was able to come up with an acronym that sounded appropriate for what the topic was. Okay, so I wanted to start by kind of setting the stage for the world that we live in and think a little bit about resilience, because, I mean, kind of going very, very big picture, a lot of what we think about when we think about formal methods is kind of how do we make systems that are bulletproof and will work in kind of every possible circumstance. And that's not the frame of mind that the world is really thinking about most of the time. And I think that comes about because for many, many years, decades, the world has functionally been actually a really safe and benign place, which is not what the world has been for most of the time of humanity. But for the last 50-ish years, it actually has been a really pretty safe place. And that has allowed people to architect and build systems for the best possible case. And that's actually worked really well. But many things are converging now that change that assumption. And we haven't really gotten out of the habit of architecting and building systems for not the best possible case. And we're going to regret that at some point in the future. We already are in certain cases regretting that. And I kind of challenge you to think about how can formal methods help us think about situations where the best case isn't the case that we should be thinking about. So I'll start with I kind of frame it as efficiency versus resiliency. We've built many of our systems to optimize for efficiency, and maybe we should be thinking a lot more about resiliency instead of efficiency. So one of the wake-up calls for that was COVID. Here, that of course, pandemic. The pictures here are from the Port of Los Angeles, where the supply chain has been optimized for just-in-time shipping for a long time, and COVID changed that. It changed the shopping patterns. People had been buying things on a just-in-time, had been buying mostly services, and with COVID, all of a sudden you couldn't do a whole bunch of the services kinds of purchasing that you wanted, and instead wanted to buy a whole bunch of supplies. You were stuck at home, and that changed what people were purchasing, but it also changed how people could work because of COVID. And that caused hundreds of container ships to back up outside of the Port of Los Angeles. I'm sure that was true around the world as well. We're seeing the same thing right now in the Strait of Hormuz, where all of a sudden you can't transit the Strait of Hormuz, and that's changing the purchasing power, the purchasing possibilities. And the COVID, at the time of COVID, something like that was seen as a once in 100-year kind of event. But now estimates are it's once in a 50-year or once in a 30-year, depending on the models. And that's because of climate change, because of habitat destruction, because species are coming closer to humanity, and diseases that used to circulate only in animals now have an easier time skipping from animals into humanity because those animals are closer to people. Also because of global travel, something that would have been isolated into a part of the world is now spanning much more of the globe really, really fast. And so something that would have been local is now global within 24 hours. Then natural disasters are becoming much, much more costly. So this graph was compiled by the Pew Charitable Trust. This is coming about because of climate change putting much more energy into the system. So the graph here on the left is the number of billion-dollar disasters from 1983 to 2002. The red is the red is 1983 to 2002, and the blue is 2003 to 2022. And the vertical is just count on the left, And on the right, the red and blue are the same time period, but the cumulative cost. So the red shows that there were 95 total between those time periods, between the 1983 and 2002, and the blue, there are 244. So from 93, like it jumped from, 96 to 244, and the cost went from, it's too small for me to see on my slide, 546 million to 1.9, sorry. Yeah, I think those are trillion. Anyway, massive increase, right? And again, because of the number of natural disasters, the number of people living in areas that are subject to natural disasters, like basically on coasts that are subject to, and this is becoming the new normal. So natural disasters, so pandemics, natural disasters, conflicts, right? We see in Palestine, in Ukraine, now in Iran. This is also, like global conflicts have doubled over the past 5 years. Then we have something that's closer to our own area of expertise, which is how we build megasystems and the growing interdependence of megasystems. So an example here is the Texas power crisis. So in power grids are amazingly complicated systems where you have to balance the amount of power that is produced and the amount of power that is created instantaneously. Like, think about that. That's an amazing engineering marvel. And in 2021, Texas had a cold snap. It got very, very cold in Texas. And this had two simultaneous effects where many, many people turned up the heat because they obviously, at the same time, the power freeze had the snap caused many power supplies, power stations to go offline because the power lines, the pipes supplying natural gas to the power plants froze. And so at the exact same time that demand spiked, supply crashed. And so the grid went out of balance. And when the grid goes out of balance, the frequency with which the grid operates starts to fall. It's supposed to be at 60 hertz, and it fell to like 59.4. And if it goes out of balance for more than like 10 minutes, the transformers basically self-destruct. And power grid transformers are like a 3-year lead time. If you want to order them, you have to call up people in Germany, I think, and order them. And it takes 3 years to get another one. And if you don't have them, like the state doesn't have power. So there's a tripwire that says like, we will shut it down. And if you do if you shut down the power grid, it takes like weeks to come back up again. And so Texas was 4 minutes and 37 seconds from the system shutting down to cause a weeks-long restart process, right? So like, imagine all of the effects you would have if Texas had no power for weeks at a time, or worse, if it had actually like the trip had failed and it didn't have power for years. Now that was a natural disaster, but we also know that adversaries could possibly have code in this system that is controlled, like, because that's controlled by software, right? So like an adversary could cause that effect to happen. And right now it's nation state level adversaries that have that capability. But in the future, you could have terrorist organizations or ransomware organizations have that capability. They don't have that capability right now, but they could. Another example is the 2024 CrowdStrike software error, right? Where CrowdStrike runs monitoring software to see if an attacker has infiltrated software, right? And they run this code at kernel level. And in 2024, they're constantly pushing updates because bad guys are constantly updating their system. So in 2024 in their Falcon software, they pushed an update and they didn't properly test this update. And this particular update was in how the pipes that the systems communicate to each other. And it's in kernel mode. And the particular file was expecting 21 files, but 21 fields, but only 20 were being supplied. So it was a parsing error. Many, many, many vulnerabilities are related to parsing errors. So and it was pushed all over the place, and when it triggered, it caused a crash at load time, at boot time. And so it took a really long time to fix because you had to you had to reboot the system, and you had to be able to update the file just at the right time in the bootload cycle. And so like the fix instructions basically said, reboot the system like 16 times. Can you imagine being the sysadmin on a critically important system and your boss is yelling at you, and like Delta Airlines was down for 5 days as a result of this problem. And the instructions say reboot the system 16 times. Like, it's just because like hopefully in that 16 times you'll eventually get fixed, right? Hospitals were affected, air traffic control was affected, financial trading systems were affected. And it was like the more advanced, the companies that had been proactive about fixing their security were the more affected systems. So these are like all examples of places where we have systems that are very, very complex, that are very interrelated, and we don't understand the full complexity of the system. So places where we need to have a better understanding of how things are going, or we could end up with catastrophic failures. Of course, like none of those were all accidental, but cyber attackers could cause these kinds of things to happen. One of the biggest ones that we've seen so far is the NotPetya attack, which was a Russian attack on the power grid infrastructure in Ukraine that escaped Ukraine and ended up traveling to Maersk, which is one of the world's biggest shipping conglomerates. They control 20% of the world's shipping. When the attack reached Maersk, in less than a minute, it destroyed 50,000 of Maersk's computers. It destroyed their entire VoIP phone system, bricked all of those devices. They lost all but one copy of the database that they use to keep track of where all their shipping containers are in the world. The only reason they didn't lose all copies of their database was because there was a power outage in Ghana. And so the computer in Ghana that had a copy of the database was disconnected for the relevant period of time. And so to reconstruct their knowledge of where all their shipping containers were and what was in their shipping containers, they had to fly down to, someone from Ghana flew to Nigeria, and then someone from the UK flew to Ghana and got the laptop and flew it back, and they reconstructed it, right? But they were paralyzed, and for more than a week, they ran Maersk through personal cell phones and spreadsheets, which is not really how you want to run a global conglomerate. And I would argue we've been lucky so far that this is as bad as it has been. Our exposure continues. Of course, it's hard to measure the degree of technical debt we have. This is one of the best sources of data I found so far, which is a report that the OSSRA report, which is published every year from 2018 to 2024. It's a survey of open source software that's used across many, many, many sectors, like basically every sector. And how they use software. And what it shows is, like in the most recent report, which was just released for 2024, shows that 97% of the code bases across all these sectors of industry contain open source, so at least some open source. And of those 97 code bases, 70% of the code in those code bases was open source. So across many, many sectors of industry, most of the code in those code bases is open source. And then 86% contain at least one vulnerability, and 81% contain a high-risk vulnerability. And I don't mean to be dumping on open source code. I don't think there's any reason to think that the open source code is any more vulnerable than closed source code. We just can look at the open source code. So there's a lot of vulnerabilities in the code that we run industry on. And I don't think there's any reason to think military national security code is any different than this code that we're looking at. Then we know that bugs in software are exploited to take over and to in ransomware attacks. This is the Mandiant M-Trends data. This is the 2026 data for that. And it shows that 32% of the time, bugs in the software are exploited to get in and attack the software. So this year it's 32%. If you go back in time and look at this data, it bounces around at the 32% point. So it's not that bugs in software aren't important. And if we could figure out how to use our formal methods-based approaches to eliminate these bugs, we would be doing a huge contribution in society to making software less less vulnerable, making it so that ransomware attackers have a harder time. Does that mean ransomware attackers and other bad guys won't have other ways in? No, of course, there are other attack vectors that would also need to be solved, but it would be closing a really meaningful threat vector. Of course, there's the guy in Nebraska. I love this cartoon, the poor little guy down there. The particular task that I'm talking about here is Lassie Colin, who was maintaining the XZ compression library in the Linux distribution. He had been working on this for a long time. XZ was a much better compression library than gzip. And then he had Jia Tang, was somebody who was working to help him do a better job. And then Jia actually had some friends who talked to Lassie, said that he was way too slow in putting in patches, and wouldn't it be better to turn over maintenance of this important library to Jia, who's been really helpful. And over time, Lassie agreed, and they turned over maintenance of XZ to Jia. Little known to Lassie, Jia was in fact putting in changes into XZ that put in a backdoor into XZ that was on track to be distributed to all Linux distributions, to have a remote backdoor into the SSH distribution of Linux. He was vouched for by like 5 other GitHub users, so there was a broad network that was saying Jia was a really good guy. These turned out to all be fake accounts. Jia turned out to be most likely some Russian guy based on the forensics of the account. And this was discovered by Andreas Friend, who worked for Microsoft, but really in his spare time, he was maintaining the Postgres library. And he noticed that there was a slight timing degradation in his Postgres library. And this very small timing degradation bugged him. And so he went to dig in, and he discovered that there was a shell in the XZ compression library, which shouldn't be there. And so he flagged this and got the whole thing taken down. But it was only because of these some guys in Nebraska, right? Lassie Colin, who was maintaining the library in the first place, and then Andreas Friend, who was this total hero, who was by himself responsible for basically saving the whole world, more or less, from having remote shell capability in a compression library that everybody, all Linux distributions. Interestingly, this was only in the binary. The open source, the source code didn't have the vulnerability in it. So if you built the tool from sources, you are fine. It's only if you use the binary distribution that you are in trouble. And then, of course, we have AI-enabled tools. We have the Mythos release that is turning out to be quite a step change in the ability of AI to find vulnerabilities in code. So this is the AI Safety Institute, the UK AI Safety Institute, measuring the effectiveness of large language models in finding vulnerabilities. The horizontal axis is the number of tokens used, and we see that as the models use more tokens, they are more effective. This is on the last ones, which is a simulation of a kind of a corporate server kind of setting, not super well defended, but breaking in does require 32 distinct attack setups. 32-step simulated corporate network attack, and it measures how many steps the models are successful at completing. Mythos was the first model that successfully completed all of the steps. It completed all of the steps in 3 out of 10 runs. And we can see clearly the trajectory of these models as they get more tokens, and as models become more capable, they are getting better and better. So that the trend is in a direction that these models will be able to find and exploit vulnerabilities. Work after Mythos was released, so this is kind of out of the box, just Mythos without extra scaffolding. Work that was released shortly after Mythos showed that if you put existing open source models into a scaffold where the scaffold does some of the work, can replicate this kind of capability. And so this capability already exists in open source models if you don't expect the model to do all of the work without scaffolding. So kind of what I want to take away from that is that our software systems are vulnerable already to hackers. They will be more vulnerable to attackers with lower levels of skill with AI-enabled tools than they currently are. We know that our software is riddled with vulnerabilities. Our authority to operate processes, particularly that I'm familiar with in the military, lock in those vulnerabilities. Pour it into the open end. The process of getting an authority to operate certificate can be super onerous. It can take like a year, so that by the time you get the authority, you are not willing to do anything that will undo your authority. And so if you find a bug or a vulnerability right after you get the authority, you're like, I'll wait till the next release process to do anything about that bug. And so you accumulate a list of vulnerabilities that you might know is exploitable. And so like, you know it's exploitable. Your adversary might know it's exploitable, but it's locked in until you redo that authority to operate process. So a process that was well-intentioned, the authority to operate process, which is intended to increase the quality, actually has the effect of locking in bad quality software. That's not dissimilar to the processes of authorizing medical equipment, for example, which has an even worse problem because the timing properties of the software for medical devices requires particular version of the software, because if you change the software, you might change the timing properties, which would be terrible. So now you're like even a worse problem where you have locked in a version of the software, which you know has vulnerabilities and might be there for like 10 years. And like the vendor of the software might not even be supporting it anymore, but you know it has vulnerabilities. It's connected to the internet because that's how you do maintenance. And if you change it, you might kill people. But if you don't change it, you might get hacked for ransomware. So all of this is a place where we desperately need to change how we certify software, how we maintain software, the pace at which we maintain software, or the level of correctness to which we produce software in the first place, so we are not vulnerable to ransomware attackers, to hackers who are enabled with things like Mythos, or the future. It's not Mythos per se, but to tools like that make it so hackers will be able to threaten that software. And I think like formal methods and the kind of tools that everybody here knows and loves are like the best tool that we have to change the threat landscape that we're dealing with. Obviously, formal methods, like this slide is not really for you guys. It's for all the people who like, what are you talking about? What is formal methods, right? Formal methods is a wide spectrum of different tools. And I don't have a particular, it's not like this formal method. It's like the whole range, like all of them are useful. They're useful in different contexts. Like type systems are formal methods, right? They are easy to use formal methods that you don't have to think about. They prove very simple properties, but still very, very useful properties. All the way up to full functional correctness, where you have a specification, you prove that the code does exactly what it's supposed to do and nothing that it's not supposed to. They're all useful. The goal is to figure out which tool or what set of tools should be using for what purpose and when, with the goal of reducing that technical debt as much as possible and as soon as possible. You probably all know about HACMs, right? HACMs was helpful in changing the conversation that formal methods is just a toy thing that researchers like to work on for fun. It actually is relevant for fixing, for real practical problems. People were shocked when HACMs proved that a quadcopter was fit for purpose, and when the red team was not able to hack into the quadcopter, my boss at the time said that the quadcopter proved that the program was a success. And that's when he told me that the director of the agency thought that the whole thing was going to fail. I was pretty shocked at the time that the agency approved an $80 million program that they thought was going to totally fail, which is like interesting. I'm sure you also know like what was actually in HACMs. The SCL4 microkernel definitely was like, that's what made it so that we could put the red team in a partition and trust the lives of the pilots with that, and do the assessment while the helicopter was in flight. People are still shocked when I talk about this result. They're shocked that it worked at all. Like you were willing to do that, right? And so like even 10 years later, that we did this 10 years ago, that you can do that, and that the tools and techniques of formal methods are up to this level of assurance. And I think that the power of a good demo is really changing people's minds and convincing people that something is possible that they didn't think was possible before. Also, other things that people are surprised about when I tell them about HACMs is that the people who did the work on the Boeing unmanned Little Bird were Boeing aviation engineers. They were not formal methods researchers. The formal methods researchers taught the Boeing aviation engineers how to use the tools. But the Boeing unmanned Little Bird was ITAR restricted and proprietary. So the formal methods engineers couldn't get access to it. So they had to teach the Boeing aviation engineers how to do it, and they could do that. So like it might be that formal methods are esoteric and complicated, but they're not so esoteric and complicated that other smart people can't figure out and how to use them. Another thing that people are surprised by is that the red team was along the journey the entire time. So they think, oh, well, yeah, but the red team only had like 2 weeks. Like, no, the red team followed along the entire time. They knew as much about that system as you could know about that system. So it's not like they only had a little bit of time. They had a lot of information about the system. So when you talk to people about this, you can tell them that the red team knew a ton about the system, and it was not the formal methods engineers who did the work. It was the Boeing aviation engineers who did this work. Be happy to answer other questions. Another thing that was really important was the parsing at the boundaries, like just throwing out bad packets at the edge, another huge, huge saver. So memory safety, verified parsing, and input validation and separation are 3 things that get you a huge return on investment as far as formal methods are concerned. Amazon Web Services learned the lesson of HACMs more immediately. They're like the one massive adoption success. I spent a lot of time as the I2O director working on how do we improve adoption. Amazon has been a great partner in helping I2O at DARPA tell a adoption story. Of course, Byron Cook went to Amazon and was instrumental in having Amazon adopt the technology. One of the things that I think is really cool about what happened at Amazon is they learned that by using formal methods, they not only got better security, they also got better schedule predictability, they got better performance, and they got better cost. So from like a business program manager's perspective, they got like everything a program manager could want. And in kind of going forward, they learned that they could be much more successful at selling formal methods on the performance, the schedule, and the cost than they could on the security. And they would often sell on those first 3 dimensions, and then they would get the security as a byproduct because nobody wanted to talk about the security failures, but they were very, very happy to talk about the cost gain, the schedule gain, or the performance gain. So let me just tell you a little bit about why they got those other kinds of gains. So they have the secure storage system, or the simple storage system, which is a simple kind of database. It's not really simple. It stores a vast amount of customer information. And it's a database that, or tuple store. And there are like 17 different kinds of systems that write into this database and read out of it. And they knew they had a bug in this data system. And they didn't know what was causing the bug, but it got patched up. So in some sense it was okay, but it bugged them that there was a bug in the system. And so they periodically went to try to find this bug, but they couldn't find it. And they had multiple Tiger teams try to go find this bug, and they kept failing to find the bug. But it complicated making any changes to this code base because there was massive amount of testing every time they went to go make a change. And there are like millions of updates a second to this data store. So it's very complicated. So eventually they asked Byron to prove the thing correct. Not Byron personally, Byron's team to prove the thing correct. And eventually they succeeded in proving the thing correct. And of course, to prove the thing correct, they had to find the bug. They did find the bug and they fixed the bug. And then going forward, every time you wanted to make a change, you had to prove that your change maintained the correctness proof. And when they proved the correctness proof, you could bypass a large amount of the testing. So you cut out a huge amount of testing. And this allowed people to make performance improvements much, much faster than they could in the past. So you got better performance and you got more predictability, and that saved cost. So formal methods allowed them to do things faster, do things cheaper, get code to be faster, and better security. So DARPA has invested after HACMs in a whole bunch of different kinds of approaches to formal methods. The CASE program looked at often security is something that happens at the very end of a system where you build the whole thing and then you bang on it with the red team and you find all the places where, oops, we didn't get security right, let's go fix it. CASE was about, could we develop a priori the statements that we would need, the properties that we need to get the security right at the end instead of at the beginning. Yeah, build them in at the beginning instead of at the end. SafeDocs was about parsing. Could we build better parsing infrastructure and or expressive languages and improve PDF, which they actually did. ARCOS was about that authority to operate. Could we do a better job of generating authority to operate artifacts from the actual software instead of having it be a completely separate process? And can we curate the documents for authority to operate, which is only partially successful? AMP was, could we, if we have a binary, and we only have the binary, and we know there's a bug in the binary, can we figure out how, and we have a patch, we know how to fix it at the source code level. We only have the binary, which in the US military happens a lot. Could we decompile the binary in a way that is targeted toward the patch that we have, and then patch the decompiled binary, so that the source code, and then compile it back down into the binary in a way that is provably not going to screw up anything else. And that was actually very successful in advanced decompilation technology a lot. VSpells was about, you have some complicated spaghetti code and you want to re-architect a part of it. So think about, you have like spaghetti parsing code and you want to, so you have like some, complicated code, and you, in there is parsing code, and you want to redo the parsing code in a principled way. Can you identify that, separate out the parsing code, redo the parsing code, and put it back in? Or crypto code, right? You have some principled piece of code that you want to architect. That's what the VSpells program has been doing, and actually reasonably successful. Harden is about identifying weird machines and identifying how to close the weird machines so that attackers can't exploit a system across multiple levels of abstraction. Provers is about automating theorem proving. Can you integrate AI into a theorem proving pipeline to make it easier to prove properties of software? CPM is about automatically inserting compartmentalization into code so that you can, if an attacker breaks into a system, they only can control a piece of the system instead of the whole thing. EBOS is about creating an electronic software bill of materials so that if you find out that a large system has a particular vulnerability, can you go and, well, if you find out that there's a vulnerability, can you figure out if a particular code base has that vulnerability, and if so, where to go patch the code very quickly? Tractor is about automatically converting C to Rust in an idiomatic way so that we could get rid of memory safety vulnerabilities in C once and for all. And then ICS is about virtual reality, and can you apply memory, formal methods techniques to to identify, could people be hacked through virtual reality systems? And then AICC, how many people have heard of AICC? Oh, interesting. Okay, so AICC started with the premise that AI would be really, really helpful to not only find vulnerabilities like Mythos does, but fix them. And we ran it in a competition style format at DEF CON in Las Vegas. And so there were, I can't remember how many teams, 8 or 9 teams. And we ran it on open source code that was selected to be representative of the code that runs in critical infrastructure. And an interesting theme, the teams that participated in the competition were very, very skeptical at first. They were like, sure, we'd be happy to run in a competition to find and fix bugs, but we don't think that AI stuff is going to be useful. We ran the competition in partnership with Google, Anthropic, OpenAI, and Microsoft, and the competitors had access to those frontier models. The competitors ran on 54 million lines of C and Java, so it was at scale. They did, in fact, find and prove vulnerabilities. So like they had to not just like say like this is a vulnerability, but they had to find and create a proof of vulnerability. So more or less they had to be able to exploit the vulnerability. But what we were most concerned about was, could they generate a patch that would fix the bug that would be acceptable to downstream partners? And we partnered with the Open Source Software Foundation, Open Source Security Foundation, OSSF, because what we cared about, like this was done in anticipation of Mythos and the ability of frontier models to like just create many, many exploits, and figuring that we were going to need to be able to fix the bugs at speed and scale. And so the reward function was very, very few false positives and really, really high quality patches. So the team running the competition planted 63 synthetic vulnerabilities so that we could score the game. But this was also real software, so we expected there to be real vulnerabilities as well. So the teams discovered 54 of the synthetic vulnerabilities, and they successfully patched 43 of them. They also discovered 18 real vulnerabilities that were verified by the software maintainers, and they patched 11 of those. So I think what's really exciting about this is not so much the finding vulnerabilities, it's the patching vulnerabilities. So, to the extent to which there are many, many, many vulnerabilities, and people are not going to be able to patch those vulnerabilities or write the patches on their own in time for the coming tidal wave or the cyber apocalypse that might be coming, this ability to not just find them but fix them could be really important. And the tools that these people built, these were not just, they didn't just like point the AI system, the models that they were getting from the frontier companies at them. They were combinations of cyber reasoning systems, which are basically formal methods tools, and AI tools at the vulnerabilities, because we were pointing, like the scoring system, basically, they had to be really high quality. They had to throw out all the chaff and produce really high quality answers. And when you interviewed the teams afterwards, the teams' skepticism had completely gone away. They were like, AI tools are super, super valuable. And it's the combination of the cyber reasoning system, the formal methods tools, and the AI tools that were massively game-changing. Okay, so I've talked a lot about DARPA. ARIA is also playing in this space. The Safeguarded AI program is working on exactly this problem of how can we put AI and formal methods together to get out better software and better AI systems, more trustworthy AI systems at speed and scale. So one of the things that is Nora here? I don't see her. Okay, her name tag is out there, so hopefully she will be here later. One of the things that Nora is working on is a formal methods AI leaderboard. And this is a benchmark. Like, how do you get frontier model companies to do stuff? You publish a really interesting benchmark and you get them to race on the benchmark. So a lot of formal methods-based things are language kinds of problems, right? And frontier models are really, really good at language problems. So right now, so could we get frontier models to be really good at formal methods-based problems? So the idea behind this is, could we create a benchmark along the lines of SWE-bench or Frontier Math or ArcAGI that measures how good are frontier models at formal methods-based problems, and get them to race on the ability to create formal methods-based problems, so that in the fullness of time, when frontier models are writing the vast amount of software, could they also be producing proofs that the code that they are producing is really high quality code that is fit for purpose? You can imagine if we have like cyber apocalypse in the future, maybe there could be pressure applied to produce code and proofs that that code is fit for purpose. And if there's a benchmark that measures how well the code that they produce is fit for purpose with respect to formal methods-based properties, that could be helping to justify that they could in fact do this. So this is one project that Nora is running as part of the Formal Methods AI program. And then another piece of work that we are funding here is scaling formal assurance with neural certificates. I know there's a PhD student, no, postdoc who is here, who is working on this project that's led by Dr. Mirko Jacobe. And this is partly, can we use AI ideas from machine learning to make to make formal methods go faster? I think that this is just the tip of the iceberg in ways in which we can leverage ideas from AI and machine learning to facilitate problems in formal methods. We have another program, Scaling Trust, with Alex Obadia. This is about the world of Moltbot, or you have many, many, many AI agents. How do you get those many, many, many AI agents to talk to each other in a secure and trusted way? This program is specifically focused on the communication piece. How do they develop protocols to talk to each other that are trustworthy and work in an environment that is not trustworthy and share exactly the right information? That you could do things like develop a custom protocol that is provably correct and trustworthy, that temporarily shares your information but is then guaranteed to delete that information, that shares only the information you want to share for only the duration of time that you're willing to share that information. When you deal with another person and you say, well, like, I'm going to give you this information but only for this time, and I want you to forget this information after that time, of course, people can't actually delete that information out of their brain. But if you're having your agent talk to another person's agent, that other person's agent could in fact provably delete that information after that period of time. So this program is looking to explore questions like that. And the structure of this program is a competition where there's an arena where agents will interact, and then there's a technical area where we will have researchers work on agents and components, and then there's a technical area focused on fundamental research. Then just kind of want to talk about, well, just briefly mention, like, I think AI and formal methods are two technical topic areas that are critically important for the future. They have complementary strengths. AI, super flexible, talks in human native forms, but not super trustworthy, too plastic. Formal methods, super trustworthy, not super flexible, not super human friendly. Putting them together, we can get the best of both worlds. I think AI can make formal methods go better, go faster. Formal methods can make AI be much more trustworthy. I think there are many, 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 many ways that these two things can be made to fit together and make each better than the other. And I think there's like very, very rich research to be done here. I think probably too much of the focus is on the AI side and not enough of the focus is on the formal method side. I mean, there are 60 people here, and NeurIPS has 10,000 people. I think is a sign of the imbalance, but I think we as a community have a ton to add. I want to just end with a little bit of communication about, or talking a little bit about how ARIA works. Like, ARIA has been in existence for only 3 years. I think it's pretty impressive what ARIA has done in 3 years. ARIA was stood up to make the world in the UK a better place, which is like just a little bit of a daunting mission statement. The vehicle by doing that is to run high risk, high reward project-based research. So every project has a North Star, a goal of what we are trying to accomplish. And doing that by advancing breakthrough science. And then after, it's like there's a science miracle we have to accomplish. And then after we accomplish that science miracle, we have to translate that science miracle into societal impact. So, and that's all done under the guidance of a program director. So we have to hire a program director, and then we have to create that North Star vision of the world could be a better place, the UK can be a better place, by creating the science miracle from some basis of confidence that the world is ready to have that science miracle. And then we have to translate that science miracle into societal impact. So a lot to do. So like unlocking scientific and technical breakthroughs that benefit everyone, particularly in the UK. So I like to think about a program has a particular time frame. So programs don't go on forever. They have a fixed endpoint. There's kind of a North Star on the top right-hand corner. And they have a certain amount of resources associated with them. And there's that science miracle. And so when the program director starts the program, they have to articulate like, why they think investment in a particular technical area is a good investment, like why there's a ripe area for exploration. That means they have to have a basis of confidence that, like, if we add gasoline right now, there's a huge potential that we might unlock some disproportionate value. So like, this is like the same thing at DARPA, like ARIA was modeled after DARPA. So when I started the HACMS program, there was the SEL4 paper and there was the CompCert verifying C compiler as evidence that formal methods was ripe to tackle real world problems. So similar kind of, those are the kind of the nuggets, the basis of confidence that there might be ripe for exploration ideas, the kind of thing that a program director would need to have as evidence for now is the time to explore that. So that's the kind of upper half. This part here is the societal impact. So it's not enough, like ARIA's job is not in fact exploring science for science sake, right? The UK has UKRI that explores science for science sake, which is super important, right? ARIA couldn't exist without UKRI doing a fantastic job. This part is we have to take the science miracle and convert it into societal impact. We need to get people to use the technology. And there's lots of different ways you might do that. We could start companies. We could license the creations to an existing company. We could change government policy. We could start a new program because it could be that it takes multiple steps to get there. But every program director is expected to have that theory of change and work out, like, if the science is successful, this is how we're going to change the UK. This is how we're going to change the world, and develop a strategy to get there. Does it require changes in policy? Does it require regulation? Does it require creating a new market? Who is going to help us do that? Because ARIA doesn't do long-term commitment. We do projects and then we leave to go do different projects. So who is going to be on the field long-term? What's going to get them excited? Why are they here? How do we get them excited? What do they care about? So we are hiring a chief translation officer at the board level, at the exec level, to work with all of our program directors to focus on that. And that impact maximization strategy is kind of what works at the interface between the science miracle and the technology translation piece to maximize the chance that we get the science miracle and then we get the translation miracle. And throughout the process, throughout the life of the program, ARIA and the program director is working to remove friction, to make it so that the people who are working on the program, which we call creators, are maximally likely to succeed at reaching that North Star, which means the program director is in the face or in the business of the creators throughout the life of the program. It's not like traditional funding where the funding agency throws the money over the wall and comes back a few years later to say, kind of, what did you do? Maybe. ARIA program directors are constantly, how are you going? What is it doing? Come to my meeting, talk to me, and assessing, like, are you on track? Is the program collectively on track to reach the North Star, which I should put a star in that corner, to accomplish what's there? And if you are on track, or if you're like more promising results, you could get extra resources. We have activation partners which are funded to help remove friction. For example, Emoto Partners is an engineering firm that is available to do contract engineering for performers, which is probably not so useful for formal methods, but there's a team on, like, the Forecasting Tipping Points group is building sensors in Greenland to focus on whether the subarctic gyre might change, which could cause massive climate change in the UK, which would be really bad. And they needed a modular battery. And the normal process for creating, like, batteries in Greenland, normal batteries don't work in Greenland. It's too cold. So they needed a bespoke battery. The normal process for producing a bespoke battery would have taken 18 months. They would have had to apply for funding. They would have had to win the award for getting the funding. They would have had to contract with an engineering firm. They would have had to iterate on that. It would have taken at least 18 months. Because Emoto Partners is on contract, they iterated with Emoto Partners three times and got a modular battery solution in 3 months. Right? So saving them an order of magnitude worth of time. And that's, like, Emoto is working with 54 different of our creators. So that's an example of how ARIA is working with our creators to remove friction. On the other hand, if you as a creator decide, like, well, I know I wrote in my grant proposal that I was going to do X, but I've decided I don't really like problem X anymore. I want to work on problem Y, which is in this other direction. your program director will say, okay, you can go work on problem Y, but your funding is staying here because we need to work on the problem that's going towards our North Star. Right. Then everything works through program directors. So it's really useful if you want to have funding with ARIA to get to know the program directors in your area of research. They are often very interested in talking to experts about what might be possible if they either to help shape their ideas on their current program or to shape ideas for a future program. If they currently have a solicitation on the street, they can't talk to you about the solicitation that's on the street, but they can talk to you about future solicitations, or you can talk to them when they are not currently having a solicitation on the street. In addition to big funding calls, they also have seed funding, so you can get funding for smaller seeds in addition to full programs. And yeah, so seed funding can be from like 50K up to larger amounts. So seed funding can be sizable. They still care about what you're doing on a seed, so like you expect them to still pay attention, even if you're just getting for a seed. And then ARIA desperately needs you to help us in order to succeed, right? ARIA has a very small staff. Like all the things that ARIA accomplishes is by people in the community, creators doing the work under contract. So ARIA can't succeed without people in the community helping us to do that. And there are many, many ways to contribute. So one is to become a program director, right? If you have your hair on fire of like, I want to change the world, this is how to change the world, you consider coming at some point in your career to be a program director. The first time somebody suggested that I might want to be a program manager at DARPA was 10 years before I became a program manager at DARPA. So like now might not be the good time for you to be a program director at DARPA, at ARIA, but 10 years from now might be something that you want to do. We do have we hire in cohorts at ARIA, and we have 2 cohorts currently there. And the third one, we are in the process of starting that hiring process. And so it will be in the fall. The finals will be in December, and we expect cohort 3 to start in the spring of the coming year. We also have technical leads, which are internal technical experts who, like program directors, are term limited. We expect people to come and serve between 3 and 5 years, and then we kick people out the door. I can talk to you about why that is if you're interested. Technical leads are internal people who can be there for a long time. So that's another possibility. Creators, like write proposals, come and get funding and help us change the world. Outside experts, when we work on new programs, we consult people out in the community. So like answer the phone call if a program director calls up and asks, like, what do you think about this? Is this possible? Is this not possible? What do you think are important areas? But also when we review proposals, when we ask for opinions on opportunity spaces, ask for opinions on program theses, when we review actual program ideas. There are many places where we ask for technical expertise from the outside world. If we ask you to serve as an outside expert and you don't want to be a creator, you can't do both, say yes. Serve as an activation partner if you want to help other people remove friction. Yeah, and help us work towards a better, more resilient world. And I think your particular skills are particularly helpful in fewer software vulnerabilities. And I think I have 10 minutes for questions.
Thank you so much. Any questions for Kathleen?
Hi, I've got 2 questions. One, I noticed that you were linking with Galwa, and I wondered, given the programs, how much is UK based and how much is able to be internationally based?
Yeah, so the UK government wants ARIA to provide value in at least 3 different ways. So the first is value creation. So that's like finding a cure for the common cold, finding a treatment for depression, finding a way to like prove all of our software is correct, right? That's like solving the science miracles and then translating that into the real world. The second kind of way is value capture, which is creating businesses out of the value creation that benefits the UK. So like the company that figures out how to cure the common cold, we actually do have a program called innate immunity, sculpting innate immunity, where if it is successful, it will in fact find a cure for the common cold, right? We have a program that is about finding treatments that will work for deep depression. So those examples are actually real ARIA programs. So the second one is value capture, which is setting up businesses that capture the economic value of those scientific investments, which would also be enormously economically valuable for the UK. The third one is by spending our research dollars in the UK. So if you look at kind of the magnitude of those, the value creation, the value capture are vast, but only accrue to the UK if we're successful. The third one of spending research dollars is tiny, but guaranteed. And so we spend about 80% of our research dollars in the UK. But there are cases where whenever we spend research dollars not in the UK, there's always an analysis that says, but the benefit accrues to the UK anyway, and we can't do the work without spending this outside of the UK. And so like in that case, it would be like Galwa has a capability and a track record in this space that we could do this right away, and we can't do that without in any other way. And the value of having, like with the UK Safety Institute, right? The UK has this reputation for working in this area, and continuing to bolster that reputation for the UK is hugely valuable, and getting this work done right now is hugely valuable. So every time we fund outside of the UK, there is a careful analysis that it's worth it to the UK to do this. Another analysis would be that there's some work that could be done, that has to be done for the program, that will be hugely more, like there's all the, like every program that gets started, there's vast expertise in the UK, but there might be some expertise that's not in the UK that we still need, that we would fund outside of the UK to complement the part that's missing. The UK does amazing work in science and technology. If you, on a per capita basis, it's third in the world behind the US and China. And if you, I mean, actually on a per capita basis, it's first in the world, which is like just unbelievable, fantastic. And on a per capita, on a non per capita basis, it's behind the US and China, which is just like, the UK is like global powerhouse from science and technology research.
Thank you. If you don't mind, another one. With the HACMs, the North Star was something like, you could have the red security team not able to break the helicopters. The sort of and you were a game changer. In some ways, it didn't succeed, in the sense that the autonomous vehicles right now are not running on verified software. But we can see some version of trajectory, and in decades' time, what's going to happen with that. From your point of view of ARIA, would you be prepared to have North Stars like the HACM's North Star, where the benefits are in terms of decades, in terms of the innovations?
No, definitely. I think most of the ARIA North Stars are in fact decades out.
Yeah.
Yeah.
So
like,
you've got a specific one to do with the end of the project, and then the focus for the future.
I think the best program North Stars are in fact kind of multi-layered, where there's like a North Star that's like 20 years out, but there's also one that's kind of 5 years out, so that you can be like, we will have something that would be recognizable as a victory at the end of the program if we're successful. And then, but it layers up to an even more impressive thing 20 years out. It's kind of like a grand slam and a single. And like you structure it so like you're working towards a grand slam, but you get something no matter what. It doesn't always work that way, but.
So your work, or the work you're describing on using AI to find and patch security vulnerabilities, I was wondering, so Frontier AI is also has a number of new attack vectors and vulnerabilities. So there'll be a perfect occasion to, as you find a security vulnerability, you introduce a hidden one. So I was wondering if there's something that is considering this work, the balance between having AI to patch, but also the vulnerabilities they're using AI to patch bring within their work and the risks associated with that, and how is that being managed?
Yeah, I mean, I think in the fullness of time, we want to work towards better and more secure software, right? And I think that there are core pieces of software where you could imagine having specifications of what the software is supposed to do and prove that those pieces of software are functionally correct and don't have vulnerabilities. I think there's other pieces of code where it doesn't really, like, it's not worth that level of assurance, and working towards having the pieces that you really, really care about be proven to be functionally correct, and identifying what those pieces are and getting those to a much higher level of assurance, and like not caring so much about the other pieces. We haven't yet gotten to the point where people care enough to get to that level. I think we might get to that level in the not too distant future. I think that also, like, not all properties are the same. I think we should be working towards memory safety for everything and making it so that it's not okay to have not memory safety, and input validation safety as well. I think we should be working towards a place where everything is expected to prove that it is input validation safety, that it handles all inputs that it's expecting. Things like that.
I was talking more about the fact that if you're using AI to explore your code, then you can attack the code as you do that. So you might not end up with securities that have been identified and patched, but you might have backdoors, for example, that has been introduced during the process that you're not aware of, because you have a prompt injection as you're doing the AI to look at your vulnerabilities. That was really what I was asking. Sorry.
Yeah. I think there that I think that's going to be a really interesting challenge as we go away from people writing code to AI systems writing code. And I think people are really poorly suited to doing code review at massive scale. And I think we should be thinking about how do we handle that mismatch? Because I think we're not going to, it seems very unlikely that we're going to end up in a world where AI systems don't write the vast majority of our code. So how do we, just given the psychology of maybe the economics of code writing, like everything I hear is that inside of frontier companies, et cetera, like they have the AI systems writing the vast majority of their code, which means it is effective for them. So hopefully we can get better at having analysis systems that find those backdoors, and or having like one AI system analyze another AI system, and or alignment systems that make it so the AI systems don't want to put in those backdoors. Because I don't see a world where we don't have AI systems writing that code.
Isn't there a efficiency versus resilience?
Yeah, I agree. But like, I mean, just from looking at the efficiency has so much weight behind it that I think it's like trying to say that like make it not happen is going to be really, really hard. So I think figuring out how to deal with it is a more likely path forward. There's in the back.
Hey, question about memory safety. So as of a month ago, you can just about get an LLM to do a one-shot lean proof of safety, memory safety, or data race freedom in certain small idealized concurrent programs. Do you have any thoughts on how you might scale that to self-driving car AIs, something like that? The unicorn question.
The usual approaches. So nothing magic. Do you have ideas?
I'm asking.
Sorry?
I'm asking. I'm just seeing if there's any work, because not easy to do. So
I mean, you guys are much closer to the recent technical work than I am. So I think the audience probably has better ideas than I do at the moment. Oh, so it sounds like somebody does, yeah.
Just so while we have you online, you mentioned sort of a relationship between ARIA and UKRI. I was kind of wondering about the relationship between, given that we're kind of NCSC funded, about the relationship between ARIA and NCSC, given that a lot of your concerns that you mentioned today were about software vulnerabilities and security in general.
Remind me of how NCSC fits in the.
They're the National Cybersecurity Center. And they fund VETS and the other research institutes.
Yeah. So are they inside UKRI or are they inside the?
They are not inside the UKRI.
Yeah.
They're alongside.
They're alongside.
Yeah.
So I have talked to them. So ARIA currently, ARIA is independent of all of we sit inside of DCIT, but we are functionally independent of all of the roadmaps so that we are able to choose what we want to fund independently. But we want to be collaborative in understanding how what we do would be relevant to other organizations, and we want to be informed of so we want to be technically well informed on what's possible and what's not possible by the researchers and the creators. We want to, as we have technical insights, and we want to understand how the research that we do would translate into the problems that the various organizations work on. So I personally yet have not particularly talked to the leadership of NCSE, or if I've talked to a lot of different people that I haven't yet solidified each of the names and the faces, but wanting to understand well what the problems are, what the opportunities are, how to take the research that we've done and translate it into problems that they care about so that we get the impact that we're looking for. We don't do classified work because of the research, because of the friction that introduces, how much time it takes to get classified, to get clearances, et cetera. But want to be informed by, if you do this, it will have this impact kind of thing. In the fullness of time, we have 7 more years on our authorization, so want to really clear that hurdle. And so in the fullness of time, that might change, but aware that the things that we are working on in cyber, for example, probably have implications for high side work, and would very much want to communicate this result has this impact and could be developed further on a high side kind of application. So apologize, I've only been in post since February, and I'm still getting used to the UK ecosystem.
Okay, thank you.